Welcome, everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to understand interval notation and identify the intervals in which a function exists, how to find the domain of a function both algebraically and graphically, how to determine how a function behaves around given values, how to determine when and where a whole or asymptote occurs, how to determine the x-intercepts of functions, how to determine the multiplicity of the roots of a function, how to sketch graphs of functions based on the characteristics of the function, how to determine whether a function is positive or negative, how to determine whether a function is increasing, decreasing, or remaining constant, and how to recognize minima and maxima of functions. How are we learning it? Through the Reasoning with Features of Functions Review Part 1 notes and the Reasoning with Features of Functions Review Part 1 assignment. When can we use this information? To understand boundaries, to determine which possible solutions fall within the boundaries and which do not, to recognize trends in graphs to determine the trends in the stock market, to examine financial trends in a business and to determine when the value might reach zero and the business goes into debt, to be imaginative in your ability to find solutions to problems when only given limited information, to examine financial statements for businesses to determine times of profit and times of debt, and to recognize the high points and low points of a given stock in the stock market. How do you know you learned it? By getting a score of 4 on the Reasoning with Features of Functions Review Part 1 assignment. Let's take a look now at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you've completed your Get It Started, we'll go over it together and answer any questions that you may have. After that, we'll go over the Reasoning with Features of Functions Review Part 1 notes, and then I'll give you time to complete the Reasoning with Features of Functions Review Part 1 assignment. Once you've completed the assignment, we'll go over it together and answer any questions that you may have. At the end of class, we'll go back over our learning goals and success criteria while you fill out your Before You Go. Your only homework for tonight is to work on any incomplete assignments that you may have. Let's take a look now at the Reasoning with Features of Functions Review Part 1 notes. The notes begin with the learning goals and success criteria. So what is an interval? An interval is a set of values which satisfy a given function. An interval can be used for any set of numbers, but for most of this unit, it will primarily apply for the domain or the x values of the function. For example, we have y equals mx plus b, which is a linear function, and it's going to go from negative infinity to positive infinity because it goes forever in both directions. So that would be an example of an interval. So interval notation is a way of writing values using the form parentheses a comma b. So where this value here, a, represents the lower boundary, so wherever it stops on the left side, and then b represents wherever it stops on the right side. So interval notation then looks something like this. So we can use parentheses or these brackets. So the brackets are used if that value is included. For instance, if it ends at 3 and it's actually including 3, then we would use a bracket. If 3 is not included, so it gets really close to 3 but never touches it, that's when we'll use the parentheses. So here, if it's less than or equal to or greater than or equal to, we use the brackets. If it's just less than or greater than, we use the parentheses. So it's not included in the set. If it goes on forever, we put infinity, and infinity is not a number, so it can't be included in the set. So it will always be parentheses whenever you see infinity or negative infinity. So if we're given this, x is greater than or equal to 3, and it asks us what is the interval, well, we want all numbers that are bigger than 3. So we know that we're going to have a minimum of 3, and it's included. So we should have a bracket with a 3 here. So that's our a value. That's our minimum. Now our maximum, notice they didn't tell us what the maximum is, so it continues to infinity. So our maximum here would be infinity. So we'd have bracket 3, comma, infinity, parenthesis. So it goes from 3 to infinity, and 3 is included, but infinity is not. Here's another example. It says all integers except negative 2. So notice now we're going to have integers on the left side of negative 2 and integers on the right side of negative 2. So we need all the integers smaller than negative 2. So we know then that negative 2 is the maximum because it's got to be smaller than that. So negative 2 is the maximum, and it's not included because it says except negative 2. So we know we're going to have a parenthesis around negative 2. And the minimum, there is no minimum. We want all the numbers less than it, so that's negative infinity. So this one would go from negative infinity to negative 2. And that's when x is an integer. Okay, we need to state that x is an integer. We need to now include the numbers on the other side of negative 2. So now we want all the integers bigger than negative 2. So we know negative 2 will be the minimum then, and the maximum will be infinity, right, because it goes on forever. So we would have negative 2 comma infinity, where x is an integer. So both sets apply for this one statement. So it says state the domain of a function with the interval negative 4 comma 0. So now we're going to take what we did before where we had it in words and had to put it into interval notation, and we're going to reverse that. So now we're given the interval and we need to put it into words. So we know it has a minimum of negative 4 and negative 4 is included, and has a maximum of 0 with 0 not included. So we could say that x is between negative 4 and 0 and includes 4 but not 0. So just putting it into words. So it says state the domain of the function with the interval negative infinity to positive infinity with x not equal to 0. So that means it's in all numbers excluding 0. So it has a minimum of negative infinity and a maximum of 0. And x has a minimum of 0 and a maximum of infinity. And notice 0 is not included, so we should have parentheses around it. So we could say then that this is all real numbers, all numbers that exist except 0. Now what if we're given a graph and asked to find the domain and range? So domain is the x values and range is the y values. Well, we can see here that this graph goes and it continues on forever this way. So it goes from negative infinity. And notice it gets really close to 3, but it never actually touches it. So its boundary is 3. So we would say then that it has a minimum of negative infinity, a maximum of 3, and it's not included. So we would have parentheses, negative infinity to 3. Now here, our range. Well, we can see that the range, it stops and has a boundary, a lower boundary right here. And we're going to call that maybe negative 3. If this is negative 2, this is about negative 3. So we'll call that about negative 3. And it goes on to infinity. So the minimum is negative 3. The maximum is infinity. Negative 3 is not included. Infinity is not included. So it would be negative 3 comma infinity with parentheses around it. Now what is an asymptote and a hole? An asymptote is a line that the graph approaches but never crosses. So an example of this would be 1 over x minus 1. And we can say that it has an asymptote at x equals 1. Because anytime the denominator equals 0, that's a spot where it would be undefined, because now we're dividing by 0. And remember from closure, if anytime we divide by 0, we have an undefined value. So it's undefined at this point, so we create an asymptote there. Now a hole is a point that is not on the graph, and because it can be factored out of both the top and bottom. So it's where the graph continues on and then stops for a second and then continues on after that. So an example of this would be x plus 1 over x plus 1 times x minus 1. And we'd say it has a hole at x equals negative 1, because this can be factored out of both the top and bottom. And then we would solve that for x, and we get x equals negative 1. So how does this look graphically? An asymptote looks like this. So we have our graph here, and it gets really close to negative 2, but it stops and doesn't actually touch it. So it just keeps going up and getting really high here, but it will never actually cross this line of negative 2. Same thing here. It gets really close here to negative 2, but never actually crosses it. Now a hole, an example of that would look like this. So we have our parabola here, and then just at this one spot, it's missing. So the graph continues and does cross, it's just has a point there where it doesn't actually exist. So how does an asymptote or a hole affect the domain? Well, we can see here that our graph goes to here, so it goes from negative infinity, but then when it gets to negative 2, it stops continuing. It stops and has an upper boundary of negative 2, and then it picks back up again. So here we go from infinity, and when we work back this way, we go to negative 2. So it has a domain of negative infinity to negative 2 and a domain of negative 2 to positive infinity. So let's talk now about how we can solve for asymptotes. Well, if we're given a function like this, f of x is equal to 1 over x minus 1, what we need to do is we need to recognize where the vertical asymptotes occur, and they occur when the denominator is equal to 0. We know this, again, because when the denominator is equal to 0, the function would be undefined. So we set the denominator equal to 0. So x minus 1 is equal to 0, and solve. We add 1 to both sides, and we get x equals 1. So this is the location of our vertical asymptote. Now, how do we find holes? We find holes when a common factor of x exists in both the numerator and denominator. So for instance, in this case, we have x plus 1 over x minus 1 times x plus 1. What we should notice is we have an x plus 1 in both the numerator and denominator, so we could cancel those out. When we cancel those out, we gain a hole and lose an asymptote. To find our hole, then, we just set that equal to 0. So x plus 1, we set it equal to 0. Subtract 1 from both sides, and we get x minus 1. So that's where my hole occurs. Now, there's a video here that shows you how to graph functions in Desmos. So go ahead and watch that video. Let's take a look now at how we can use Desmos to graph any function. So in order to do that, we're going to go to desmos.com and go to Graphing Calculator. And here we can type in an equation. So let's say that we have a linear function, which is y equals 2x minus 5. And notice it graphs it for us. It creates this graph here. We can type in any kind of function. We can do an exponential. Y equals 2 to the x power minus 5. That's what it would look like there. We can type in a quadratic. Y equals 2x squared minus 5. And see exactly what that one looks like. We can do trig functions. So y equals sine of 2x. And that's what it would look like. We could do logs. Y equals log 2x. And see exactly what it looks like. So we can graph any one of these kinds of functions, and it will do it for us in Desmos. If there's ever any difficulties with what you're trying to do, so let's say I'm trying to do a squared term, so y equals x squared, and you're not sure how to do that, this little keypad here will click out, and now I can change it to be squared. I can change it to be any exponent here, so I can click on this and make it to the 6th power or whatever I want it to be. So you can use this any way you want, and this is how we can use Desmos to graph any function. Now, what is end behavior? End behavior is the behavior of the graph as it approaches positive infinity or negative infinity. So end behavior can be written as this: as x approaches some value, and it doesn't always have to be infinity or negative infinity. It could be some value. It could be the asymptote. So as it approaches, and this negative sign means that it's approaching from the left side. So as it gets close to that point from the left side, y is approaching some value. The other version would be as x approaches that point from the right side, then y is approaching something. So an example of this would be here. So we have our function here, and we have a vertical asymptote here at negative 2. So we're going to say then, as x approaches negative 2 from the left side, what is y doing? Well, as we get closer to negative 2 from the left side, we can see that y is increasing exponentially. So y is approaching infinity. So as x approaches negative 2 from the left side, y is approaching infinity. Now, if we look at as x approaches negative 2 from the positive side, so from here, so from the right side, so as we get closer to negative 2, what is happening with the graph? Well, we can see it's going up and up and up, so y is also approaching infinity. This is how we can describe end behaviors. Now, there's a video here that shows you how you can use a spreadsheet to find values. So go ahead and watch that video now. Let's take a look now at how we can use the spreadsheet to answer questions. So on this one, the formulas are already given for you, so you just have to copy and paste these in. So this would be for question 2A on the function descriptions part 1 assignment. So I'm going to go ahead and copy this here. So I copy it. I'm going to come down and put equals and then paste it. And it should ask if you want to autofill. Go ahead and click the check mark. So now we have all of our values here. Now we're going to do it for the denominator as well. So I'm going to go ahead and copy this, come down, put equals, and then paste it. Again, it asks if I want to autofill. Click the check mark. And then lastly, we're going to go ahead and put the numerator over the denominator. So we're going to copy this, put equals, and then paste it. It asks if we want to autofill. We click yes. And notice it appears in red. These would be your answers. So these are the answers that you will put into your Desmos activity. Once you're done with this one, we'll go to the next question and do the same thing with each of these columns. So I'll copy it, put equals and paste, and then autofill. Copy, equals, paste, and then autofill. And you'll do that for each of these questions and then move those answers into Desmos. So this is how you can use a spreadsheet to solve math problems. First, what is a zero or an x-intercept? The x-intercept is the x-coordinate of a point where the graph crosses the x-axis. So if we look at this, we have a line here, and it crosses right there. So in this case, we would say that our x-intercept is at about 2. And we also call these x-intercepts zeros or roots. So they're called all of these different things. So how do we determine where an x-intercept exists? X-intercepts occur when y equals 0 and x is not undefined. So for instance, if I have y equals x minus 1, well, I just want to plug in 0 for y and solve for x. So I plug in 0. Now I'll add 1 to both sides, and I get that x equals 1. So that is the point where my x-intercept occurs. So if we put it into coordinate form, it would occur at 1, 0. Now, what is multiplicity? Multiplicity is the number of roots a polynomial function has at the same x-intercept. So multiplicity occurs when there is more than one root at the same x-intercept. So an example of this would be x minus 1 squared. Well, we should notice that x minus 1 squared is the same thing as x minus 1 times x minus 1. So we can solve this because we just need to set it equal to 0. So both of them would have to be 0 because they're the same. So we'd add 1 to both sides and we get x equals 1. So that would be our root, x equals 1. But it's occurring twice because we still have both of these here. So we would say that my x-intercept is at x equals 1 and has a multiplicity of 2. So how does this help us, knowing the multiplicity? Well, the multiplicity can determine whether the graph will cross the x-axis at the x-intercept or just touch it. If the multiplicity of the function is even at the x-intercept, so it has a x squared, x to the 4th, x to the 6th, etc., it will touch the x-axis but not cross. If the multiplicity is odd at the x-intercept, it will pass through the x-axis. So even multiplicity. So notice here we have a point here, and it has a multiplicity of 2 or 4 or something like that. It's going to touch, bounce back, and come back up. So anytime we have a multiplicity that's even, it's going to touch at that point and then bounce back up. Now an odd multiplicity is going to pass through. So we have a x-intercept here or a 0 here at -2, and it's going to pass through and keep going. So even multiplicity, odd multiplicity. Now let's talk about positive and negative functions. And we're not really talking about positive and negative functions as a whole. We're talking about the intervals where these things occur. So functions are said to be positive on a given interval when the range of the function or the y values is above the x-axis. So when the graph is showing above the x-axis, that's where the function is positive. Now they're negative on a given interval when the range is below the x-axis. So what does this look like? Well, we have a graph here, And notice my graph goes here, it passes through the x-axis, comes down, starts to come back up, changes again, and becomes above the x-axis. So in this case, we would say that the positive intervals are the green sections. So here, the graph is above. Even though it's going downward, it's still above the x-axis. So up until this point right here, it's positive. Then once it hits this point, it starts to become negative all the way until it hits this point again. Once it hits this point, now it's positive again. The purple area would be considered the negative intervals, where it goes below the x-axis. So even though right here it changes direction and starts going back up, it's still negative until it reaches this point where it actually crosses the x-axis and starts to work above. So now how do we determine where an interval is positive and negative? Well, if we look at this graph here, we have a graph where it is negative here all the way from negative infinity all the way up until it gets to negative 4. And then it becomes positive after that. Now, over on this side, we have it being negative from negative 2 all the way until this point here. We'll call it negative 1. It may not be exactly negative 1, but it's close. So it's negative from negative infinity to negative 4, and then from negative 2 to negative 1. And then it becomes positive from negative 4 to negative 2, and from negative 1 to positive infinity. So that's how we can use graphs to determine the intervals on which a function is positive or negative. Now, what is a sign chart? A sign chart is used to determine on which intervals a polynomial function is positive or negative. So we talked about positive and negative intervals. Now we're going to use a graphical display to show where it's positive and where it's negative and when it changes between them. So the top of the sign chart represents the positivity of the function. So is it positive or negative? So we have positive, 0, negative, 0, positive. So that means it goes from positive to positive, and these are my x-intercepts. The middle of the sign chart represents the change in positivity, so it's just this little graph look here. It almost looks like a number line. And then we're going to put lines here to represent the x-intercepts. And the bottom represents the values. So where did these occur? So maybe I have an x-intercept at 1 and 3. So it was positive until it hit 1. Then it crossed and went negative. And then it crossed again here at 3 and then went back positive. So that's what this sign chart is telling me. So how do I create a sign chart from the information that I have on this? Well, I know that it's going to change 3 times. So it has an x-intercept here, and then an asymptote here that's going to change things, and then another x-intercept. So I'm going to go ahead and put these values in. So at negative 4, negative 2, and negative 1, that's where things change. So I was negative to start. So that negative goes here. Then it turned positive. So I put a positive here. Then on the other side of negative 2, I started negative and then turned positive. So it goes just like this. So this would be the sign chart that represents this. Now there's a video here that shows you how you can use Desmos to create your sign charts. So go ahead and watch that video now. Let's take a look now at how to create a sign chart using Desmos. So we're given a graph here and we're told where it crosses and we need to create a sign chart. So first of all, we need to break this up and show where the roots are, where it changes and goes from positive to negative. So I can see that that's at 1 and 3. So I'm just going to go ahead and draw a line here and a line here. And I'm going to call this 1 and this 3. So all I did was write on it by clicking and holding it down and drawing my stuff in. So now I have 1 and 3. I know that at 1, I'm even. I'm not positive or negative. So I'm neither positive nor negative, so I'll put a 0 there. Now on the left side of 1, I am positive. I'm positive all the way up until I hit 1, so I'm going to put a plus sign here. Then between 1 and 3, I'm below the x-axis, so I'm going to call that negative. So this is negative, minus sign. And then on the right side of 3, I go back to being positive, so I put a plus sign. So this is how you can create a sign chart using Desmos. Now, what are the different types of functions? So functions are said to be increasing when they are moving towards infinity as we work. So they're rising or going up. So during that time, we would say they're increasing, as if the line or the curve is going up on a certain interval, then it is increasing. Decreasing would be the opposite. So as we work from left to right, if the function is going downward, then that is considered to be decreasing. And lastly, if it's not increasing or decreasing, so it's a flat line going horizontally, then we would say that that is constant. So here's some examples. So we have a graph here, and as we look from left to right, it is obviously going upward. So this is an increasing function. This one here, as we go from left to right, is going downward, so this is a decreasing function. This one here is a flat horizontal line, so this is a constant function. Now, not all functions are just one thing. So for instance, we have a parabola here. Well, we can see that on the interval negative infinity all the way until 0, it is decreasing. But then on the interval 0 to infinity, it is increasing. So this is both increasing and decreasing on certain intervals. So we would just need to define those intervals then. So how can we determine the interval then? So the question here is, where is it increasing? Well, we can see that from here, from negative infinity all the way to negative 2, it is an increasing function. So from that, we can state that from negative infinity to negative 2, it is an increasing function. Now, likewise, it's going up here as well. So from negative 2 to positive infinity, we are also increasing. So we have two increasing intervals for this function. Now, what are minima and maxima? Well, a maximum is the largest y value that corresponds to an x value in a function. So what that means is, as I look at the graph, where is the highest point that it's reaching? And if it never stops increasing, then we would call that infinity. But if it goes up and then bounces and comes down, then whatever that highest point is, that's our maximum. The minimum is the exact opposite, so it's the lowest value. So if it goes down forever, then we would say our minimum is negative infinity. But if it bounces and comes back up, we would call that our smallest value, whatever that point is. Now, a maxima is a plural form. So we could have a function that goes up, goes down, goes up, goes down multiple times. And each time it goes up, that is considered a maxima. Now, it may not be the ultimate maximum, but it is a maximum. So that represents that value. The minima is the same thing, but just the low points. So for instance, we have a parabola here. Well, we can see that it has a minimum right there. It does not have a maximum because it goes up forever. So it has a minimum here, but not a maximum. Now this one goes up and then comes down. So it has a maximum, it stops there, and the minimum just goes to negative infinity. So it only has a maximum here. Now, what is a relative minimum and maximum? So like I said earlier, we have these different minima and maxima. So on this question, it asks, where is the relative maximum and what is the relative maximum? So the location is written as x equals a. So we just need to write out the x value. Well, this is a minimum here, right? And then it goes on forever. So this is not considered a relative maximum. This is an infinite maximum. So my relative maximum is right here at this point. So I'm just going to write down the x value. That's all I need to put. Now the maximum value is the y value when x equals that. So this becomes the y value. So right here's my point. So my location would be the x coordinate, which is -1. So I would say x equals -1. Now my actual maximum is the y value at that point, which is 1. So I would say y equals 1 is my maximum. Now if we look at this for the minimum now, again, we write the location as x equals a and the minimum as the y value when x equals that coordinate. So here we have a relative minimum right here, And we know that the location, the x-coordinate is -2. So x equals -2 is the location. And then my actual minimum will be the y value at that point, which is 3. So I would say y equals 3 is my minimum. Let's take a look now at the reasoning with features of functions review part 1 assignment. The assignment begins with the learning goals and success criteria. If we scroll down, we can see the questions. The first one says, given the equation below, does the function contain an asymptote or a whole? Well, we should be able to see that we can factor out an x squared out of the top. And when we do that, we get x squared times x plus 1. And x plus 1 is in both the top and bottom, so we have a whole. The next one says, what is the equation for the asymptote for the function below? So what's going to make this 0? Well, if we put -3 in here, -3 plus 3 is 0 squared, which is 0. So we need this to be -3, so x equals -3. And we'll continue to answer all of these questions until we get to the end. Once you get to the end, go ahead and click Next. This will take you to your Before You Go. Go ahead and fill out your Before You Go and then submit your work on Google Classroom.